All right, this is another video on work, but this is specifically looking at the work done in terms of pumping water in or out of a container. And we'll do a cylinder, we'll do a cone, and then we'll do both a sphere and a hemisphere and kind of take a look at what those look like. Okay, so in general, work done is still, the work done is still the accumulation of some force over a distance. In the previous video, I did springs, I did the leaky bucket, and I did like pulling a rope. And as you pull the rope, you're pulling less and less rope, and so the force changes. So the force is some function of X. It's very similar in this case, and what we're going to say is the force we're overcoming is the weight of the water. And so let's just start out with the easiest case right away. So we have some cylinder of water, okay, and it's not actually all the way full. The water level is here. Okay, so the water level is 4 meters. The height of the actual cylinder is 5 meters. The radius is 2 meters. Okay, and the density of water. Okay, so water is 1,000 kilograms per cubic meter, and that's a mass density, right? Kilograms is the unit of mass, 1,000 kilograms per cubic meter. And if you want to know the weight density, you just multiply by 9.8, right? Because that's how you find the weight, you know, mg. And so that makes that 9,800 newtons per cubic meter is then the weight density. Newtons is a weight, and then it's a density because it's divided by cubic meters. Okay, so what we want to do here is to figure out the work required to pump all of this water. Again, all of this is full of water here. That's all water. 4 meters of water in a cylinder 2 meters in radius, and we're going to pump all that water out. So we're going to take all of this water and pump it to the surface and then let it drain out some hose or something. Okay, and the work done is still this. Okay, so how do we go about doing this? So the work done is we are going to, okay, so what's the force we're overcoming? Well, the force we're overcoming is the weight of the water, and what we're going to do is we're going to break this up into discs. Let's do that up here. Let's draw this picture again. So there's our cylinder, and we're going to focus just on one particular layer. Okay, give that a little thickness. Okay, so can you see how that would be a disc of water? Okay, the disc has a certain radius, which is 2, and the disc has a certain height, which we'll call y. Okay, the disc has a particular volume. The volume of the disc, which we know is dV, right, some individually placed volume. dV is pi r squared times dy. Pi r squared is the area of the disk, and then dy is this thickness. Okay, so that's the volume of the disk. Well, we know then the weight of the disk should be the volume of the disk times the density of the disk, which we know in this particular case this is water, and the density is 9,800. Okay, so what we have here, this number represents the weight, which is a force, right? It's the weight of each disk. Okay? And now we need to multiply by the distance we need to move each disk, which then gives you the work done on each disk, and then we sum up all of the work required to take all of the disks up, right? That's what we're doing. We're going to take this water and break them up into a whole bunch of really small discs, right? We're going to take that disk of water, cross-sectional area pi r squared, thickness dy, and then we're going to pump it out, and then we're going to pump another disk out. We're going to pump all the disks out, and then we're going to empty our tank. Okay, this is the weight of each disk, the volume of each disk, times the density, right? This is cubic meters times newtons per cubic meter gives you the newtons, meaning the weight, which is the force of gravity that we need to pump out, and then how far do we need to move it? Okay, so each disk is at a height of y, but we actually need to move each disk this distance. Well, this distance is 5 minus y. Again, the whole cylinder is 5, and so this distance is 5 minus y. That's the distance we need to move each disk. Okay, and then what are we going to let y vary from? Well, y is the height of all of our disks. Well, the disk at the very bottom of our tank has a y value of 0, and the very top disk has a y value of 4. So we're going to integrate from 0 to 4. Think about what all this says again. The work done is the accumulation of all the work for each individual disk. Each individual disk is the weight of a disk, which is the volume of each disk times the density of each disk times the distance each disk has to move, and then we need to sum up all of those, and we're letting y vary from 0 to 4, where y is this distance, right? When y is like 0, then we're talking about the bottom disk, and how far do we have to move it? Well, 5 minus 0 is 5. We got to move that particular disk 5 meters. Well, when like y is 3, we're talking about the disk that's way up here. 5 minus 3 is 2. Well, yeah, if that disk is at a height of 3 already, we only need to move it 2, which is what this is doing, and we're going to let that vary from 0 to 4, meaning the bottom disk we move 5, and the top disk we actually only have to move 1. Okay, think about all that, and then this is just some integral. This is just you type in, and you're like, oh, what is r? Well, remember, r is a constant in this case. The next thing we do, it'll be some function, but this really is just 2 times 9800 times 5 minus y dy. You can just type that in your calculator, and you go ahead and you get 1.478 times 10 to the 6th, so 1.4 million joules. And again, this is in the real units: kilograms, meters, newtons, joules. That's how much work is required to pump the water out of this cylindrical tank. All right, let's do a different one. And unfortunately, calculus books are pretty stupid, and they use feet and pounds a lot. So my next 3 examples will all do in English units. Okay, so let's take a cone, and let's say that the cone is 4 feet by 6 feet. 4 feet by 6 feet, and so we can set up a proportion here to show that r is to h as 4 is to 6. So we know that the r value of any one of the disks that I'll show here in a second is just 2/3 the height. And again, what we're going to do here, we're going to take this cone, and that's full of water, we're going to pump it out. We're going to take that disk again, so there's that disk. Okay, and the disk has an r value, but that disk and that disk, not only are they at different heights, thus they need to pump a different distance to get out, right? This disk we got to lift this much to get out, and this disk we have to lift this much, but each disk has a different radius. However, the radius of each disk is related to the height of the disk. Again, our coordinate system kind of looks like this in this case. Okay? So we'll think about this again, and we're going to follow the same thing. The work done here is the integral, and we can talk about the bounds here in a second, and it's pi r squared dy, right? That same thing. The cross-sectional area of this disk is pi r squared. The thickness of that disk, right, the height of that disk is still dy. The density here is silly since we're in foot-pounds. Water is 62.4 pounds, which is the English unit for weight per cubic foot, which which is silly, but that's just 62.4. It serves the same purpose as this 9800. And then times how far I'm going to move it. Again, this particular disk has a height of y. The whole thing is 6. So then I need to move this, right, to pump that particular disk out. If the whole thing is 6 and that's y, then I need to move this thing 6 minus y. Okay? So then think about that integral. I'm actually going to have to move, I'm letting y varying from 0 to 6 because this is full of water, right? Totally full. Right? It's full. So 0 to 6 of pi, except r is some function of h. Right? The h and y, hopefully you're okay that this is the same thing. So r I need to replace by 2/3 of y squared dy 62.4 times 6 minus y. Again, think this through. This is the volume of each disk. Each disk's radius changes as y changes, which is important, right? It's a function. Over here, this was easier because the radius was always 2. Here, the radius of each disk changes. You can see that there's a small one there and a bigger one there, and the bottom one, you know, even gets smaller as y changes. When y is small, so is the radius. As y grows, so does the radius, and it always grows in this proportion because of similar triangles. Again, this is just similar triangles. This triangle and that triangle are the same in terms of similarities. This is to this as this is to this, which means that's true. So this is the volume of each. That's the volume of each times the density. Volume times density gives you force. Force times distance gives you work. Sum up all the works. And so at this point, you really are just typing this in. This is just some integral that your calculator can do. The 2/3 squared ends up being a 4/9 pi 62, and then y squared times 6 minus y. Integrate, and again, you can just use Math 9. And then you go ahead and you can get 9409.7, and the silly unit is foot-pounds. That's the work done to pump out a full cone full of water. And again, I did a cone here, I did a cylinder here. This one, the cylinder wasn't the same, so like this bound and this number aren't the same because this is the distance I have to pump it, but that's how full it is. And over here, the 6 and the 6 match because it was full. Okay? So those are kind of the two classic ones, a cylinder and some sort of cone, but we can do other ones. And the next two we're going to do is a hemisphere and a sphere. And they're a little more complicated, but still doable. Okay, so let's say I have this tank, and it says hemispherical tank. So it's going to sit like that. Again, it's this hemisphere that's sitting in this plane. Hopefully you can kind of see that. Okay, and my water source, the water source is, I'm going to draw that again. The source of the water, I'm just going to draw the two-dimensional view of that. Okay, the water is all right here. The water source is right on the ground. So it's sitting on the ground, but the water is right there. And I want to pump this thing. I want to take the water and I want to pump it and I want to fill this hemisphere. And I want to figure out how much work is required to fill this hemisphere. Okay, so let's get some details about the hemisphere. The hemisphere does have a radius of 6 feet. And that's going to be important. Okay, we are going to fill it with water, and so water again has a density of 62.4 pounds per cubic foot. Okay, so now I want to do the work, and so what you have to think about is this circle. So what's the equation for this relationship when you look on that base circle? And again, think of an equation for a circle. It's x squared plus y squared equals r squared, so then x squared plus y squared equals 36. Because what happens here is that when you break this up into disks, just like the cone, right, we need to fill this thing. So some of the work will be taking the water and making that disk. And the disks, like the top disk is different than the middle disk, which is different than the bottom disk. They're all different in terms of their radius. So the cross-sectional area. Certainly the work done is very similar in terms of its the accumulation of the cross-sectional area of each disk times the thickness of each disk times the density of each of the substance times the distance you've moved it. Okay, in this case the distance is going to be y, and we'll talk about why that's true in a second. So integrate pi, now r of each disk changes. Now what is r? Well, r ends up being x. Think about it. That's the radius of each disk, which is the x value of each disk. And so you come down here and you solve for x. X equals 36 minus y squared square root. Okay, think about why that's true. But this x value here changes for each thing. So think about when y is 0, what's x? X is the square root of 36, which is 6, right? When y is 0, you get this disk at the bottom, which does in fact have a radius of 6. As y grows, x gets smaller and smaller and smaller, right? If you get higher and higher and higher, each disk gets tinier and tinier and tinier in terms of its radius, where its radius, again, is equal to x. So our radius here is then the square root of 36 minus y squared. The nice part is the square and the square root cancel. dy times the density, and then if this is my y value, right, that's the y value, that's the height of each disk, what do I need to do for each disk? Well, I need all the disks to vary from 0 to 6. So height here is just y. I need to move each one of these disks, that's the weight of each disk, and I need to move them varying from y. Some I need to only raise a little bit. I need to take the water and only put it to there. Some I need to put to there. Some I need to put to there. And I'm going to let the y vary from 0 to 6. And again, that's the work required to fill a hemisphere when the water source is at the bottom and I need to fill it. Okay, and so at this point, this is just typing this in, and you get 20,217 pi. That time I left the pi out. Foot-pounds of work. Okay, so that's a hemisphere example. Very similar to a cone. This time I was actually filling it rather than pumping it out. I was pumping it in, and again, the work done is the accumulation of the force, which is the volume, times the density, is then the weight of each water, times the distance I need to move each part of the water, and then I integrate from 0 to 6. All right, the last one is a little tricky, and again, this one's going to be a hemisphere. Okay, so you got to think of this coordinate system. This coordinate system kind of messes it up. So we have a hemisphere sitting there, and it's only half full. So, okay, so my water is sitting there. It's got a radius of 8 feet. It is water again, so the density of water is 62.4 pounds per cubic foot. And it's only half full. And what we want to do, oh, no, we're not doing water actually. My bad. I typed it in that this was oil. And oil is 50 pounds per cubic foot. Okay, so I changed it up. I made it oil just because I already have the numbers all worked out with 50. So let's use 50. And it's half full, and we want to do the work to empty it. Okay, we want to take all of this oil, and we need to pump it out, and we need to pump it out at the top. So we're going to take all of this and get it out of the top. There's some hole here we're going to have to pump it out of. Okay, so let's think of this circle. Now, this particular circle here is a little dicey because on the last example, the circle already lied in the plane. But here, this circle is shifted up, so we need to shift it. But we know how shifting works. I just need to shift this up and put y minus 8 squared equals 64. Again, I'm taking this equation represents this particular circle. Okay? and the circle is above. The center of the circle is at the point 0. It's centered on this x-axis, but here it's shifted up, and then the radius is 8, so then I get a 64 here. And again, then the work done is very similar. The work done is the accumulation of pi r, and again, what's r? R is this distance. That's x. So if I solve this for x, I get 64 minus y minus 8 squared, square rooted, but then I'm going to square that. Pi r squared dy. Again, that combination right there is the volume of each disk. That's dV times the density, gives me the weight of each disk, and then times the distance I need to move each disk. Okay, let's draw that picture again, just to make sure we have this down. So there's my cylinder. It's half full, so let's look at a disk. Let's look at that disk. Again, that particular disk of water has that as a radius, which is its x value. Its x value is given by this. If you tell me the height of that, I can tell you the x coordinate of that based on this circle. I think that blue circle. Okay? And that's the density, so that's the volume of each thing, right? The thickness of this little red here, that little bitty thickness here, that's dy. Okay? And how far do I have to move it? Well, I need to take this particular disk all the way to the top. Well, this distance is y, so this distance is 16 minus y. Okay? This is, if it's got a radius of 8, that's y equals 16. I got to pump it up to that. So the distance I have to move each one of these guys is 16 minus y. And what am I letting y vary from? Well, y is the height of each disk, and each disk goes from 0 to 8 since it's only halfway full. Okay, halfway full, so I'm letting all the disks vary from being right at the bottom all the way to halfway full, which is a y value of 8. Pi r squared dy, right? Every one of these is pi r squared dy is equal to dV. That's the volume of each one. The volume of each one, each disk, times the density of each disk is the weight of each disk. The weight of each disk is the force. The force times the distance you have to move each disk then gives you the work done by each disk, and then you sum them all up. And at that point, you just type this in. This is just some integral, you know, the square and the square root cancel, and it leaves you with something that's pretty easy. And what you get is 589,781, and I went ahead and multiplied the pi in foot pounds, which is the English unit for work. Okay, so I did a hemisphere, a sphere, a cone, and a cylinder. I did things that were half full. I think that first one was like 80% full. I pumped something out, and then actually in the hemisphere I pumped water in. They're all very similar, but here are the pumping problems.